You might think I'm crazy, but I'm going to do Chapter 4, Problem 31, 34, and 63 all in one. Because it turns out they're all actually the same problem, just with different angles. One of them, Problem 31, has got a mass A, up on a horizontal, smooth, which is code for no friction, horizontal surface, and it's got a rope tied to it, and that goes over a pulley, around the pulley, and down to a second mass B, hanging over. This is problem 31. Problem 34 has a pulley with one mass hanging on one side, one mass hanging on the other. Let's call them mass 1 and mass 2. And this pulley is nice and frictionless and perfect, and the cable is light and inextensible and all those nice simplifying things. That's problem 34, and this is actually Atwood's machine, after the Reverend George Atwood, who measured G effectively using this system. Well, no, I'm sort of extending simplifying problem 34. It's a little more complicated than this in the book. But then there's also problem 63, which has a ramp and a mass 2 on it, and it's got a rope tied to it that goes up to a pulley and around that pulley, and there hangs on the other side mass 1. Now these problems are all really the same, because in all three cases, I've got one mass hanging straight down, and another mass that's either on a horizontal surface, on an inclined surface, or also hanging straight down. In other words, if I consider this angle theta to be the angle between the horizontal and the ramp that the second mass is on, then this is general theta. This could be any angle. This one is theta equals 90 degrees. In other words, the ramp is a vertical wall. And this one, theta, is 0 degrees. It is a perfectly horizontal surface. So if you imagine over here, back to this one over on the right, if theta were 0, then this surface would rotate down to become perfectly horizontal. That's what this one is. A flat ramp. It's not much of a ramp. It's sort of a weird way to put it, but you get what I'm saying. It's a ramp that has no inclination to it at all. This is a vertical ramp. And then our last case is somewhere in between, miscellaneous. Theta greater than 0, but also theta less than 90, because this is the one where theta is 0, and this is the one where theta is 90, and this was, so how do they do that? We would say 90 is greater than theta is greater than 0. Okay, let's get down to business. Let's do the general case. We're going to look at this guy and show what the two cases are. Do the general case of theta and plug in theta equals 90 and theta equals 0. Okay, we've got our ramp, and it's at theta degrees with respect to the horizontal, and we've got a mass on that ramp, mass 2, and it's connected by a light inextensible string around a pulley to mass 1 that's hanging over on the other side. And there's our pulley. Okay. free body diagram. Mass 1. It has attached to it the light inextensible string. So it's experiencing force of tension upward. Downward, it's experiencing its own weight, M1G. And for the purposes of this problem, that's it. Those are the forces on M1. If we isolate M2, put it on its incline, there is a part of gravity down the ramp, FW, and I'll call this axis in a minute X, I'll explain that, and up the ramp is force of tension. There's M2's situation. Now it's also true that there is on M2, there is an Fn. And if I were being really careful about this, I would say that this has actually got FW. The full weight is purely vertical. But what I was starting to allude to is the fact that weight has a component that is against the ramp and a component that is along the ramp. And this is what I had just called FWX a moment ago, and this guy is what I will say is FWY. And as we've discussed in class, this angle theta, the ramp with respect to the horizontal, that angle theta is the same as this angle theta in here. I'll leave the geometry to you, but notice that if the ramp went down to flat, then this angle would close up to be 0 as this angle closed up to be 0. Just as a way to think about that. Okay, so FWY is right here, FWX is right here. And that implies, so there's our free body diagram. Got all my forces accounted for. Now, as ever, our next step is to create a coordinate system. Now, I'm going to say that up is plus x over here for mass 1. And since if mass 1 goes upward, goes in the direction of plus x, then M2 goes down the ramp. So I'm going to bend this axis around the pulley, and I'm going to say that this is plus x as well. That allows me to say, for mass 1 over here, that the sum of the forces in x are plus Ft, because that's pointing in the direction of x, minus the weight of mass 1, M1G, because that's pointing in the direction of negative x, and that, of course, equals M1A. And that takes care of the forces on mass 1. This is the analysis for mass 1. Okay, now from this guy, mass 2, over here, the sum of the forces in x are minus Ft, because Ft is pulling up the ramp in the negative x direction, plus the part of weight that's along the ramp, FWX. And those together equal M2A. Now, that completes step 3. I have Fnet equals MA for mass 1, and I have Fnet equals MA for mass 2. So typical in these problems when we have masses connected by a tensile element like a string or a cord. Probably the easiest way to do this thing is to use this system of equations. This guy from mass 1 and this guy from mass 2. Solve each for ft so that I can substitute directly. So from equation 1, I have ft equals m1a plus m1 plus m1g. And from equation 2, I have ft, I'm being a little crazy with the algebra here, but I think I can do it, fwx minus m2a. Done. And now, because I have ft equals this thing and ft equals this thing, I can set these two things equal to each other. I do want to do one more thing down here, though. Fw is m2g. That is, Fw for mass 2 is m2g. The part that's along the ramp is opposite theta, so Fwx is m2g sine theta. That is, the part of Fw that is parallel to x, that's m2g sine theta. So I've got m2g sine theta, not equals, minus m2a. That equals ft. So I'm just going to set this thing equal to this thing, since those are both equal to ft. And then I'm going to get, I'll solve for a, because it's so typical that you'll be asked to find the acceleration of the system